So, my pleasure to welcome Professor Michael Fitz from UCLA to our today's WINLAB seminar. So the title and the abstract were actually distributed a couple of days ago. First of all, I would like to apologize for a late announcement of the talk. So, but I hope everybody really interested made it here. So I would just read a brief biography of Professor Fitz, and then he will have the podium. Professor Michael Fitz received his BEE degree, summa cum laude, from the University of Dayton, Ohio, in 1983, and his MS and PhD degrees in electrical engineering from the University of Southern California in 1984 and 1989, respectively. From 1983 through 1989, he worked as a communication systems engineer for Hughes Aircraft and TRW Incorporated. In 1989, he ventured into academia and has been on faculty at Purdue University at the Ohio State University. He currently is a professor at the University of California, Los Angeles. Professor Fitz's research is in the broad area of statistical communication theory and experimentation. He is a recipient of the 2001 IEEE Communication Society Leonard Abraham Prize Paper Award in the field of communication systems. Professor Fitz's research group currently is interested in the theory of space-time modems and operates an experimental wireless wide area network and a space-time coding testbed. So, Professor Fitz.
Thank you very much. It's a great opportunity to be here at WINLAB. It's certainly something that's been around and been a player in wireless communication since I started as a junior faculty. So this is my first visit here, so I'm excited to be here. When I thought about giving the talk today, I sort of wanted to touch on a lot of things that I do because I have fun doing them, so I like to talk about them. And so I thought this particular topic would be good because we get to talk a little bit about channel estimation, which is a little bit about wireless channels. And we don't do channel estimation unless we want to do coded modulation on these channels. And as well, sort of some interest currently with the 802.11n, the new wireless standard. And in the end, I can pull it all together with the test bed that we've put together to sort of test out these different algorithms. So that's sort of a flavor for the talk. We have the Unwired Laboratory, and I have to give credit to my graduate students for coming up with the neat little name, which stands for something like UCLA Wireless Research and Development Laboratory. But fundamentally behind the neat acronym is really I have a philosophy about doing research that I sort of, the more that I'm working with my children in grade school, realize that it's fundamentally how science should be done. I guess I keep reading my kids' science textbook and learning about the scientific method. And what I'm really saying is that at least for the first probably 7 years of my academic career, I was on this path where I would come up with some theory and then I would implement it in software, theory, implement it in software, and I never really had the experimentation to map it back into what, does this theory really work in real life? I mean, sure it works in simulations, but the simulations can often be cooked to make it work, right? We all know that. So the idea is that, after I got tenure, I could think about these things, and I started saying, can we get an experimental system together, and can we actually do a scientific method, which means having both the loops of implementation and standard simulation kinds of things. And so that's just sort of philosophy. Hopefully it'll come out in this talk. So what am I working on? List of topics in this area, and the one I'm going to concentrate on is the channel estimation, synchronization, and some of the issues associated with wireless LANs in terms of the channel estimation and synchronization. So how do we estimate channels? So typically we want to decode in the presence of a random channel in wireless. And so there are really, as I think about it, there are three ways that you have to do this. One is a transmitter reference. So the idea is you send a preamble or something like that, and then you do your channel estimation off that preamble. The other is you do some kind of very complex joint demodulation and channel estimation, and that's got much better bandwidth efficiency because you don't have to waste data training, but it has the problem of complexity. Typically, it grows, usually grows exponential in the amount of smoothing you want to get. And then the other is to look at non-coherent. So non-coherent is somehow come up with a model for the channel and then do some GLRT kind of thing that allows you to decode and detect based on this channel model. Okay. What are the goals in channel estimation? The goal is really, sort of the standard thing you learn in your first graduate course on communications is the idea of differential encoding and decoding. So I like to think about channel estimation as, can you beat that 3 dB penalty that you typically get from differential encoding and decoding? And so that's sort of where I like to set the boundary. If I'm not doing better than 3 dB from perfect channel estimation, then I might as well just do differential encoding and decoding. Okay? Typically the idea is we want to get some kind of, something closer to 1 dB of degradation in channel estimation. And the big thing that I want you to realize, which will be important later in the talk, is if somehow your channel estimation doesn't quite work right, or you've got some, model mismatch or things like that, you can have an error floor develop. Even though you get very high signal-to-noise ratio, you're going to error floor out at some fairly low, a fairly high error rate because of this mismatch in channel estimation. So we're going to try to, basic.
What is this SNR? What is this? Is that a rule of thumb?
Yeah. Okay. Yeah. So I guess what I'm saying, I didn't really say that, but if you want to achieve about 1 dB degradation in a wireless channel, or within 1 dB of perfect channel state information, then you typically need what I'll call an estimate signal-to-noise ratio. It's about 5 times EB over N0. So you want to get about a 5 times smoothing in this estimate to get about 1 dB of degradation. So.
You mean a reference to the information avenue?
Yes.
You want
yes.
like 5 symbols, basically.
Yeah.
So
for
example.
For example, yes.
That's you give that as a rule of thumb, or?
Yeah. That as a rule of thumb. So it's fairly, constellation independent, unlike the additive white Gaussian noise channel.
Is this like your experimental observation, or is it some papers that have been written in this topic?
I guess a combination of both, right? I mean, you can do the analysis to show, assume that both of them are complex Gaussian, you can do the analysis to show that it comes out that way, as well as just a lot of observations. All right. So what are examples of transmitter reference? Well, I think anybody who understands the standard probably has seen transmitter references. So there's preambles, mid-ambles, pilot carriers, pilot codes, pilot symbols, and the really only when I think about transmitter references, I only think about essentially you just have to have the orthogonality to the data symbol, so that essentially you can process the data and the pilots independently. First grab your pilots and do your channel estimate, then process your data. And that's really the only criteria that I think about when I talk about transmitter reference. The nice thing about transmitter reference is, especially if we believe that our noise is Gaussian and our channel is Gaussian, i.e. Rayleigh fading or Ricine fading or something like that, then you're really trying to estimate a Gaussian process embedded in Gaussian noise. And so the nice thing is that turns out to be a linear filter. And so we can do linear interpolation filtering, and get the optimum performance. So that's sort of another nice thing. So this is typically, frankly, the block diagram of almost, if you assume this Rayleigh-Ricine model and the Gaussian noise, your channel estimate is going to take your observed reference signals and then just do some kind of linear filter. The form of the linear filter, of course, has to take into account the statistics of the channel. Right? If you want to get the optimum, you have to have the statistics of the channel to do that optimum. But the nice thing is, if you have that statistics, then it is a linear filter. Okay, big equation. What's the real take-home example from this? Well, here's X is my transmitted signal, and all I really want to say here is if you have a wireless channel, there are 3 things that impact the received signal you're going to get, which is Y of t. And that is where you are in space, where you are in frequency, and how much time delay you have. So these are the 3. When we think about wireless channels, we want to think about what happens in space, frequency and in time, in time delay. And these are going to be the parameters that we want to take a look at, because what we're trying to do, I mean, think about what I'm going to talk about here is I'm going to talk about, you know, space, time, frequency coding, and space-time frequency channel sampling, and then interpolation of that and trying to get channel estimates. So in order for me to, you know, go back to this previous slide, in order for me to come up with some kind of model for the statistics that I can form these linear filters, I have to understand what's going on in space-time and frequency of, oops, wrong way, of the channel. Okay, so this is one particular model. This is the discrete time model, where I have MP paths and a different delay spread, different angle of arrival, and, you know, different offset and things like that. So I think this is, you know, for WinLab, I don't have to spend a lot on this talk. You're all more experts on it than I am. So in the time domain, the big thing that I want you to realize, because this gives me a lot of insight into the problem, the big thing I want you to realize, in the time domain, my received signal, and if I concentrate on the flat channel, okay, you can think about, you're getting a multiplicative distortion. That's the sum of sinusoids, okay? So if I want to figure out what the fading is, and I know it's a sum of sinusoids, my statistics are only a function of how big my Doppler spread is and things like that. And I can compute, you can compute these out and do this. So the idea is that you will have the fading as a function of time, as a function of carrier frequency, as a function of the speed of the nodes in the environment, and it's a function of the angle spread that you have at the receiver. So if you have a very small angle spread, you want to have a very big Doppler spread, and things like that. Okay, so why is that important? Well, that's important because essentially I've got a band-limited process. No matter what it is, it's going to be a band-limited process. Okay? And what am I doing if I think about setting out pilots in the time domain? What's really pilot processing? It's somehow sampling a band-limited process. Right? That's all it really is. So if I sample a band-limited process, if I sample above Nyquist rate, then I can reconstruct that process. The higher I sample above Nyquist rate, the more smoothing I can get and more noise reduction I can get. Yeah, you had a question.
But to let your Nyquist criteria allow for full reconstructions, you need both what's in the future and what came before the.
Absolutely. So we'll talk a bit about that. So.
Causality.
Yeah. So I mean, typically, if you can do anti-causal filtering, you should do it because you get much better performance. You know, so that's at least the systems we implement. We do as much, you know, what I'll call anti-causal filtering as possible. So.
But then it pays off to oversample beyond Nyquist, does it?
Yes. In fact, if you would go and look at sort of the classic papers in this area, there typically tends to be an optimum point, and that optimum point is a trade-off between your loss in EV over N0 due to having pilots in there, right, that aren't transmitting any data, and the amount of noise smoothing you get. So there's typically some bottom of the bowl point in terms of bit error probability performance for that optimum insertion time or insertion, you know, frequency or whatever the kind of thing it is. So there's clearly an optimum. The nice thing about that optimum, it's a function of all your models and everything, but it's usually a pretty flat bottom, so that, you know, you can pick your values of your insertion period without causing a whole lot of degradation. I mean, if you choose it in a reasonably smart way. So.
And also, it depends on the how much look ahead you have. So if you're doing non-causal filtering, you usually, like, you know, you store some data and then you try to estimate something which is in the past. So there is this look ahead, and I think it's also somehow factors in. So longer it is, of course, better performance for causal filtering.
Yeah, I mean,
but there will be a delay.
Yeah, yeah. I mean, we typically have always done sort of a symmetric filtering, so we look as far ahead in the future as we do in the past. That's not our tip, unless we're constrained by finite packet size. You know, if you have a finite packet size, then you obviously can't look back in the past or over the past to the end of the packet, right? Or in the frequency domain, you have a certain number of subcarriers. You can't go outside of that band to get estimates. Okay, what about the frequency domain characteristics? The big thing that I want to say is what causes fading in the frequency domain. It's delay spread. Okay? And notice that's different from what causes fading in the time domain. Okay? The time domain was, angle spread and vehicle motion and those kind of things. So there's sort of two independent characteristics, what happens in the frequency domain and what happens in the time domain for the most part. And the other thing that I want you to realize is this time delay, when we translate it into the frequency domain, turns out to be a sum of sinusoids as well. Right? So the delay spread, when I look at it in the frequency domain, turns out to be a sum of sinusoids. All right? And the interesting thing is that, all your intuition that you have, everybody, at least for me, it's much easier to think in the time, as a sum of sinusoids being a time domain signal, and I'm filtering in the time domain, I'm sampling in the time domain, because that's what we learn as undergraduates. But the only point of this slide is to really show that, hey, frequency domain fading is also a sum of sinusoids model, okay, but it's, the time is now frequency. And you get a very, here's the time domain characteristic of, I think this is a standard Jakes model, and this is some, Salehi-Valenzuela model or something like that, and it also has a very similar band-limited characteristic to it. So the point that I want to make is all the intuition you have from time domain filtering, you can immediately translate it and use it in a frequency domain. Again, what's the important characteristic? Think about delay spread as being Doppler spread. Okay? If you've got that one-to-one analogy, then you understand everything you have to know about filtering in the time domain. Excuse me, filtering in frequency domain. Okay, so what this says is there is an optimum Nyquist sampling in two dimensions. Okay? So the best thing to do is, make sure you're sampling in this dimension at Nyquist rate and in this dimension Nyquist rate, and you can actually, have some nice, what is called checkerboard pattern that gives you good estimation. Notice this is much different than what's done in the standards. Today they typically have, we'll talk about what happens, but they don't. They have a much different pilot sampling system. I'm not sure why they chose to do that, but they're the standards and I'm not, so that's what that is. The other thing that I'll just say is we'll perhaps talk about this a bit. When you get to the edges, both in timer and frequency, the idea might be that you want to sample more at the edges to give you a little bit more smoothing in that dimension, because you can't use that anti-causal characteristic of this. So this is typically a well-designed packet system would have taken into account this edge effects. All right. Now, of course, we want to talk about space, because that's really what I'm interested in. So what are the important characteristics of space? The important characteristics of space, I want you to realize, is exactly the same as the time variation. Okay? Why is that? Well, you get time variation by your antenna moving in space. So clearly, if I'm going to move in space, I'm going to have the same things impacting performance. Okay? And so the only thing I want you to realize is, as you do your design of your pilot symbol, processing and all that things, just be aware that you could have, interaction between space and time. And I think the best way to show that, at least, here's the traditional spatial standing wave that shows how the thing varies as a function of space as you move around. So this is, I think everybody has one of these pictures. And this is one that I think is a little bit more interesting. So this is 3 antennas, and it's showing the received signal to these 3 antennas as they're moving in space. Okay, so the bottom axis is time, the y-axis is amplitude, and what you're seeing is essentially this pattern moving through the same spatial fading phenomena, right? So in other words, there's a particular fade in space at this point, and that antenna goes through it here. And because that antenna's fixed position away, after it moves a certain amount of time, the second antenna will go in, and then the third antenna. So this is just an example, a very graphic one that I think shows us very clearly that space and time can be correlated, right? Because time is movement through space, and that's the important idea. So these characteristics need to be thought about when doing estimation. Okay, so what is different from Mimo channel estimation than Siso channel estimation? The big difference is that we've got a mixture of all my transmitted signals to all my received signals. Okay? And that mixture causes a little bit of problem because it distorts things up a little bit more. But the other thing, it also produces a lot more channels. Okay? So if we think about it, if we have a 3x3 system, I don't just have 3 channels to estimate, I have 9 channels to estimate. Okay? So it's sort of a, this growth in the number of things that have to be estimated, and hence the difficulty of the problem. I'll say that, designs of my preambles or designs of my pilot patterns, that's a issue of observability and how you design that, and that can be done. And it turns out, unless you have really strange operational characteristics, in almost all cases, some kind of orthogonal sequences across the antenna is the best pilot pattern to use in that case. So the nice thing is using these orthogonal sequences can oftentimes, especially in flat fading, can break this down into a bunch of Siso problems. But even if it's not, flat fading, then this orthogonal sequences still work best out of all the possible sequences. Okay, so this is sort of my quick overview of wireless channels and how it impacts channel estimation. So we've got some sinusoids model for propagation in the wireless domain, and that produces time, space, and frequency fading. And the big thing I want you to come away with, just to be aware of if you pull out nothing else from this talk, is that space and time have correlation. Okay, frequency seems to behave fairly independently of the other, and the big thing that I want you to realize is once you understand that you've got this sum of sinusoids model with a fixed bandwidth, you can use that parameterization to help you do your channel estimation, because that will give you some models to base things on. Okay, so now I'd like to switch into sort of the wireless LAN mode, and in wireless LAN, at least as my outside looking into the standards, there seem to be 2 important modes of communication. One is the data messages, which typically are very long messages. And the neat thing is those long messages can be protected by some very powerful code, capacity approaching code. There's also a lot of service messages, AX, NAX, RTS, CTS, those kind of things. They're much, much shorter. I think the standard calls something like 14 to 20 bytes in length. And they need to be protected by some much shorter block length code. Okay? I think these are 2 different design paradigms that require 2 different design solutions. And not only that, how I do channel estimation and pilot symbol insertion is much different in the long block case than it is in the short block case. So we're going to take a look at those 2 situations and throw out some possible solutions and open some things up for discussion. So what I'd like to do is everything I'm going to talk about in this talk is going to be for a 4x4 system. Okay, I think the .11n standard has 4x4 as only optional, but realize anything that I talk about in 4x4 works in any other case as well. Okay, it's just, I didn't want to have 500 different plots to show you. And there's going to be 3 things that I'm going to look at. The standards want preambles. Okay, there's no way we'll, if you're going to work in the standards, there's no way that they'll go away from preambles. Okay, I'll just do this because my contract is paying me to do it. But I think it's a dumb idea, and I don't really, I try to encourage people not to do preamble-based estimation, but I can't do anything about it. And then what I'd like to do is, after we talk about preamble-based estimation, is to look at long packet and short packet-based estimation and how they're different and how you might approach that problem in a different way. Okay, so preamble-based estimation is nice because there's no delay needed in decoding. The architecture is very simple, and I think that's about it. What do I mean by a preamble? Here's an example, blue being the pilot symbols, red being the data symbols, and so on a 4x4 channel, you could do something, you could do 4 channels of preamble followed by your data packet. Or, in fact, you can do 2 channels of preamble and followed by the data packet. Okay? You just have to design your preamble symbols a little bit different. Okay? So this is what we mean by preamble-based estimation. Okay, so I'd like to, again, we're going to target in this case, the .11n standard, and we need to sort of look at the design criteria of the .11n standard. And essentially, again, when I talk about filtering in frequency domain, I have to know what the biggest delay spread is. The biggest delay spread, they have all these different channels, A, B, C, D, E, and F, and the biggest one is F, and in fact has a delay spread of over 1,000 microseconds, I think. Excuse me, 1,000 nanoseconds. 1,000 microseconds would be killer. So basically 1 microsecond delay spread, essentially. And the idea is that I would have to get spacing in the frequency domain for Nyquist rate with that to be about 1 every other subcarrier in frequency. Okay. For the preamble base, that's not important, but when we go to these more efficient short packet base, you'll see how that comes in.
So these channels are for different scenarios? Like
Yeah.
Channel F is outdoor.
Yeah, I think channel F is Starbucks sitting out on a corner thing, and then they have, and then I think B is very, very short delay spread, and that corresponds to typical in room, and then they have all these other things. They all have their own spatial characteristics as well. I'm not completely familiar with all of them, but not that much. So the thing I'll say is also it's hard to get an antenna orthogonality in the frequency domain because since your channel's growing significantly in the frequency domain, the orthogonality doesn't hold, and so you're going to get ICI, and we'll show how that impacts performance. Okay. So here's an example of the 4-symbol preamble for a 4x4 case. And all I did here was take a very simple block-coded scheme and look at the performance. And so what I'd like you to realize is we're doing 3 of the standards models, D, E, and F. And D, E, and F, perfect channel state information for these kind of block codes. They all lie right about the same value. There's a little difference as you get out to higher signal-to-noise ratios. Diversity impacts different in each of the systems. And what I'd like to say is that, perfect channel state information with this 4-symbol preamble, we can get within a dB of ideal channel state information, okay? Except in channel E, okay? And we have what you can see is the building up of an error floor in this case. And what happens is we've modeled the channel as being from channel F. So we built our Wiener filter based on the statistics from channel F. And when channel E came along, lo and behold, they weren't matched, and we get an error floor. Okay, that's a problem. So the one takeaway from this that you should get is if you do your job well, you can get within a dB like we want to, and if you don't do your job well, you could produce an error floor. So we need to concentrate when we do our job on being robust to the different characteristics of the channel.
How do we know whether we are close to Starbucks or whether we're indoors?
Well, I'll eventually get there. We'll have a detection problem that answers that for you, right?
Okay.
So.
So you need a bit of coffee bean.
Yeah.
Right.
You'll see there's a coffee bean in the equation that works. All right.
This is after the channel decoding?
Yes. So this, like I said, this is a very simple block code, space-time block code.
It doesn't have the clip.
Right. It's a very simple space-time orthogonal block code. I'll show you.
LVPC shouldn't have a significant clip.
2 slides from now, I'll show you an LVPC code. Okay. Just to show that these same observations work for very powerful codes as well. Okay. So now I'm going to the 2-symbol preamble. So realize I've got 4 antennas, okay, that I've got to train across. So sort of the standard rule of thumb, everybody, I call it the urban legend, is you need to have the number of symbols equal to the number of antennas you have. Well, that's not true if you've got some redundancy in the frequency domain. You can train with a shorter preamble. Okay, but you see clearly here that, yeah, everything works except now we've got a bigger gap. Okay, and that bigger gap is due to the fact that we've got this, because we don't have true orthogonality in the frequency domain, we've got some interchannel interference causing a bit more degradation. So it's like 1.5 dB when we make a fair energy comparison, but everything else holds the same. Okay, and then to answer the last question is, do these results hold about the same when we use more powerful codes? And the answer is yes. You can see there's still about, this is an LDPC coded system, and a 4x4 with the MMSE and successive interference canceller, and the gap is still about a dB. Okay. So and these are all using the same channel estimators in both of the coded modulation cases. So I should comment that this code was designed by Rick Wessel and my colleagues at UCLA. I think is part of one of the standards being proposed right now. This was a fascinating thing for me, and I'll just bring it up. I don't know if we'll do I don't think we'll do a whole lot more with it, but just an interesting thing. So LDPC, I would think when somebody said I designed an LDPC and we use it on this particular channel, okay, that must be as good as we can get. And it turns out we had looked at these, what are known as threaded algebraic space-time codes. They're very short block length codes, but they're designed in a bit more powerful way than the orthogonal codes. They require a spirit encoder to work. And if you look, let's just pick a frame error rate at 10 to the minus 2. That's at about 8 dB. And if I look at LDPC at 10 to the minus 2, I'm at about, somewhere around 10 or 11 dB.
Is this fading?
Yeah, this is the complete .11n standard channel model. So it's a very frequency rich scattering environment. And not much time variation, a little bit, but not enough to make any difference.
But are these like paths fading really? Or
Yeah. It's all really fading.
And the previous slide before this.
Oops, did I go back?
This is BR, right? Okay, that's different.
No, I'm sorry.
No,
No, this is frame error rate,
Right.
frame error rate, and frame error rate.
No, the one that you showed was BR. That's
So I'm making a fair comparison here. The LDPC code was frame error rate, and the task code was frame error rate.
Yeah, I was confused with the slide that was previous to this one, which that bit error rate, which wasn't very good.
But it's also, I mean, it's not going to be much better because it's a short block code, right? It doesn't get any frequency diversity.
Right.
It's just, we just were trying to put something together to test these ideas before we went to the trouble of implementing a whole LDPC decoder. So this was very confusing to me, this supposedly 2 dB offset between these task codes and this LDPC code. And I said to myself, why would we have this 2 dB gap? And it turns out it has to do with MMSE and sort of suboptimal front-end processors for LDPC, and the fact that we're doing no iteration between detector and decoder. Okay, so what we've done is some experiments where we've done a map detector front end and then some iterations, and you can get back this gap between TAS and MMSE. So the point that I want to make here is there's a very important cost complexity performance trade-off that's not clear. Spirit encoder is much more complicated than an MMSE front-end processor with the successive interference canceller. So you get that 1.5 dB at a price of complexity. Okay, and that's sort of strange because this isn't really essentially an uncoded system. These block codes are, but because you use the spirit encoder, you get this gain. If you would do something similar for the LDPC, you could gain it all back and then some. Okay, so far, the best we can do is about 0.5 dB or dB better than the task codes. So that's an example. Well, I guess I showed the map here. So essentially, doing map gets us back to where we want to be. Much less data in this one. This takes the spirit encoder takes a long time to run. This takes, basically, I think the particular graduate student working on this is not going to graduate by the time the simulation gets significant data. Okay, so I was very surprised by this idea of task codes were better than LDPC, and the idea is that again, it's a cost complexity trade-off, performance complexity trade-off. Okay, now I'd like to go into what I would consider to be more optimal designs for the frames of channel estimation in this kind of environment. So the idea in 802.11n is they're going to have a legacy preamble. So if any node is there, A or G or whatever, they have to tell them, I'm going to transmit. Even though I'm going to transmit Mimo and you can't understand the thing I'm saying, you still need to shut up during that time. Okay, so they got to tell everybody to get off the air so that I can do my Mimo transmission. So the idea is that everybody's at this point have already gotten synchronized. It has time synchronization. You don't need to follow it with another preamble to do your channel estimation. You can in fact do some kind of pilot insertion into this system where you're in fact satisfying Nyquist in this domain and this domain. I show blocks of 4 in this case because we need to train in the 4 channels that we have. This is again a 4x4 case. So that's why we think it's a smart idea to put 4 blocks in time, because time is the slowest varying dimension. So we can get near orthogonality and good performance by going into the time domain. And so this is an idea of a sort of a checkerboard pattern for space-time frequency that we think makes a lot of sense. The idea is that's great is that it subsamples our channel. It's much more efficient. In fact, I like to make the following comment. If I compare this design to 802.11a, I have the same number of pilots, but I'm tracking 16 times the number of channels. So there's I think a powerful statement about how efficient use of resources is going to help you do a much better job of getting the performance. Let's see, is there anything else I want to say on this? I think the only thing is that this block, this kind of thing can track and interpolate frequency selective fading, time selective fading, and even I know graduate students don't like to think about these things too often, but phase noise and frequency offset are legitimate problems in these from the standards point of view. Okay? And so that's sort of a neat thing about this design. And the idea is, again, you can design, again, we went back to these simple block codes, and you can see, using this very bandwidth efficient preamble, we can again get within 1 dB or 1.5 dB of optimal performance. Okay. So again, I like to say Nyquist is my friend when I design these things, because that's essentially what you're doing, is doing Nyquist in time and in frequency. So the big thing that I want you to realize is, we had robustness is a big problem, right? When we were mismatched in channel, if we have the right channel, we can get within a dB and a half of the performance ideal channel state information. But if we don't have the right channel, we can have this error flow and have significant degradation. So, we don't want to just plug in our Wiener solution, because there could be problems with that. And so we have to somehow figure out a design methodology that gives us robustness and to all the parameters that we, if you think about it, there's a vast variety of channels that you could be out there, and you want to find the right channel estimator, this right linear filter, to estimate that channel. Okay? So before we go on to our let's see, how am I doing on time? I've got 15 minutes?
No, you can continue.
Okay.
So we usually, since we interrupt the speaker, so the time is it's a soft resource.
Okay, all right. So, I think. All right, so before I go on and talk more about the robustness issue, I'd like to come back to the short packet idea. And so now what we want to have is very short bandwidth efficient packets that can do RTS, CTS. And those are, like I said before, 14 or 20 bytes in length. So the idea is that we need to both train the channel and send this very short packet of information across in as bandwidth efficient a way as possible. Okay? And that's sort of the goal that we're trying to do here. And we shouldn't do, we shouldn't do LDPC. That just doesn't make sense when we got 14 bytes. Okay? So we should do some, maybe some space-time code or something like that makes some sense into this case. The other thing is that has to really be understood is I have to be, since this is an acknowledgement message, this acknowledgement message has to work for any of the rates that we're going to go, anywhere from 1 bit per channel use up to 20 bits per channel use. It has to be reliable at all those signal to noise ratios. So it has to be very, very reliable, as well as having very bandwidth efficient use of the channel. And so the idea, here's an example of what we did for the 4x4 case, is essentially because of the big delay spread the channel F could have, we actually have to get Nyquist rate to be every other frequency. And so what we can do in this situation is have every other frequency with pilots, and then every other frequency with data. And that way, in 4 symbols, we can get both data channel estimation and data decoding of a 14 to 20 symbol packet. Okay. So what I want you to realize is that you may not think that's all that impressive, but this essentially is the same packet length as the training preamble in the 4 antenna case for the .11n standard. So what the .11n standard would do just for channel tracking and channel estimation, we're doing both channel estimation and data decoding in this particular example. Okay, what's our performance look like? Okay, this is with a particular what often is known in literature as the super orthogonal code. So it's basically a concatenation of a TCM with a super orthogonal block code. And again, what you can see is very, very good performance, very low EB over N zeros, much lower than those high data throughput rates that we were doing before. And again, you can see even though we're subsampling the channel quite significantly, we're still within 2 dB of perfect channel state information. Yes?
So it's as if you were using, if you had, say, 64 frequencies, so you were just sending data on 32 of them and you were using the other thing. But you assume the adjacent ones have similar channel characteristics. I mean,
right, so we're assuming we're using this band limited characteristic of the delay spread to give us some kind of smoothing across frequencies to allow us to do that. Right, so
shouldn't you have like if you're half of the time you use data, half of the time you use packets, isn't that 3 dB loss right there?
Except that I don't, that's assuming that I'm only not smoothing across frequency, right? So if I go back, if I'm just using this to make this estimate, then I've lost 3 dB. But this one, this one, this one, and this one are all related to this one, right? So I can use smoothing across frequency to make better estimates of my channel at all the in-between times. So that's where I get the gain in terms of signal.
You're not comparing to sending only data and having the channel on.
I think his question is about the number of degrees of freedom which are being raised.
right.
But actually, that's only for
Okay,
example. It will follow by a few chunk of data.
Yeah, so let me just say that if I have perfect channel estimation, this is where this would lie with this thing. So what I'm saying is that by using the channel estimation from the preamble, based on that, then I'm 2 dB away from that.
But you assume the channel model. Your estimator knows the channel model to achieve the smoothing.
Yes. So you sort of have an idea of the intercarrier interference.
In a real system, somebody would have to estimate the statistics of that channel.
And I will get to that in 5 slides. Thanks. Okay. This is just to say that similar things can be done with 2 antennas. I have to make the preamble 3 symbols long because to get all the training and stuff in there, but nonetheless you can do similar things. Okay, so the preamble insights so far. I'd like to say the urban legend, we don't need a preamble length equal to the number of transmit antennas, okay? If you've got an OFDM system, you can train in the frequency domain the channels as well, okay? We have this loss of orthogonality you need to be careful about, and the frequency domain interleaving of data is possible, but we, again, we see a bigger gap when we do this than we did from the other case because I'm losing half of my power in there and half of my ability to interpolate the channel. Okay, pilot processing, pilot insertion really has to be determined by the worst case. I mean, you could adapt in real time the pilot insertion rate if you knew the delay spread characteristics, but in fact, I think that's one of the modes in the N standard, not pilot insertion rate, but they're actually adapting the cyclic prefix, or making it shorter to get more bandwidth efficiency. So those are clearly options that you could do, but the insertion is determined by the worst case delay spread. The other thing is that the pilot processing can be adaptive to the current channel, right? So I need to know what the delay spread is or the Doppler spread to make this. And so the goal that we're trying to come up with here is, can we somehow use this preamble or these pilot patterns that we know to simultaneously estimate the channel as well as the optimum filtering we should do in the channel? And surprisingly, the answer is very simple, and it's a very simple yes. Okay, that surprised me. It's very nice work by Wei-Jin Zhu, one of my graduate students. So the key insight I'd like to make from this particular plot is, so if you go talk to signal processors, is, oh, you've got some unknown channel, let's just do a maximum likelihood estimator. Well, the maximum likelihood estimator lies here, and all these Wiener and filtering coefficients for all the different channels lie over here. Why is that? Because you've over-parameterized the problem in the maximum likelihood case. Okay, you've assumed sort of the maximum number of paths. Even though the majority of them might be 0, there's still noise in estimating those. Okay?
Excuse me, Mike, what on the...
I'm sorry. It looks like the labels got left off. This is frame error rate versus signal-to-noise ratio. Again. So the other thing I want to point out is that the best you can do is different by the amount of delay spread you have in the channel. So the more delay spread you have, the less frequency domain filtering you can do, and the worse degradation you're going to have. Whereas if you have a very small delay spread, which is channel B, you can actually get a half a dB or 0.7 dB in performance improvement, if you know what the channel is.
So Mimo thinks there's more paths than there are.
Exactly. So, and again, I pointed this out earlier, but I'll just point it out again. If we get it wrong, we pay a big penalty. So there's two things. We want to estimate what the channel is, do a good job of it, but we can't get it wrong, because if we get it wrong in a bad way, then we get much worse performance than the little bit of, we're looking to gain 0.7 dB, which is an admirable goal, but if we get it wrong, we lose many, many dB, right? That's not a good trade-off we want to make. So we need to get it right and get it right accurately. Okay, so what is the approach that we've done? The approach is actually very simple. We quantize the channel. We say it's one of 6 delay spreads. I think the Wei-Jin picked 10, 200, 400, 600, 800, and 1100 nanoseconds. Okay, we said the channel is one of those 6 things. And not only that, but we're going to assume a uniform power delay profile across that channel. Okay? Now that doesn't match anybody who knows anything about propagation, which all of you know a lot because you're at WINLAB.
Actually, collectively, we know a lot, but it's all embedded in language.
Okay. You know that the uniform power delay profile isn't a very good model, but the interesting thing about the model is, think about it this way. It's like having a band. I like to think about it as modeling the filter as being band limited, ideally band limited to certain amounts. When we build the interpolation filter for that ideal band limiting, any multipath that's less than that will get passed through with no distortion. Anything out will be perfectly attenuated. Okay, so it's sort of like modeling everything as being, perfect bandpass processes. And so you would think six models, that's not going to be enough. But in fact, it is the case that it is enough. Okay, so what I'd like to do is, the standard 802.11 way of doing channel estimation is assume no correlation across subcarriers, and you just basically smooth at that subcarrier. And that gives you this kind of performance. Okay, this is a 20 dB signal-to-noise ratio. If you do the maximum likelihood estimator, yeah, you get better performance, and you get something like this. Okay. If you do the Wiener filter, the right Wiener filter, assuming the correct number, I should say the right delay spread, but with this uniform power delay profile, you get much better performance than the maximum likelihood, but clearly not as good as the optimum Wiener filter. Okay, so why? Because your statistics aren't perfectly matched, right? That's exactly.
Some kind of MSE as a function of something?
I'm sorry.
It's another-
I don't know what. It must be a Windows to Mac thing. All the labels got off. Yes, this is mean square error versus pilot position across the frame. So let's see, across the OFDM frame there are, let me get this right, 53 total subcarriers with the middle one not being used. That's why there's these little bumps in there in these estimations. So so you can think about this as frequency versus MSE. At your edges, you're clearly going to have your worst performance because there's nothing to interpolate on from the side. Okay. Thank you.
Seems like a lot of the gain is from interpolation.
Yes, exactly. That's what it is. And so, you know, and in fact, what we'll see, I'll go to the next slide, I think. Oops. Let me go to the next slide, and I'll make the final point. The difference between the best filter and the quantized filter is actually very small, you know, a very small amount of dB. And so by quantizing to these 6 paths, you're really not going to lose that much performance you know, you're going to lose tenths of a dB, not half a dB or anything like that.
But these 6 paths are all equal strength.
No, I'm sorry. I should say there are 6 different models that we're postulating could be there.
Okay.
There's actually, I think, in the way that Wei Jun did the testing, he was assuming there's 50 paths uniformly. Yeah, 50 paths uniformly distributed in that delay spread.
Some of these results are simulation. Are there any experimental that you're showing not only?
Experimental in terms of?
You were showing some experimental blocks in the beginning.
No, we'll get to the experiment. I mean, we haven't done any. We haven't put any of this on the test bed yet, so we'll have. I have nothing to report on test bed results, but we'll show a little bit of test bed pictures just for fun later. Okay, I want to go back to this. The neat thing that I want to say is we've got a hypothesis test. Okay, the hypothesis test is which one of the 6 filtering criteria are the true hypothesis. Okay. Well, it turns out if you plug in, go to your detection theory class, plug in all the estimates. It turns out it's a very, very simple form, right? I mean, you look at this and you say, oh, that's not so simple, but you know this is the correlation matrix. You know the correlation matrix. That's the hypothesis. It's a certain correlation matrix. So the only thing you have to do is you have these pre-computed correlation matrix, and you have to do a Hermitian form with that pre-computed correlation matrix, and then you just find the biggest one of those, or the minimum of that. Sorry, argmin, argmax, whatever, whichever one you're going with there. So it's a very simple hypothesis.
Why is the data?
Why is the data?
Yeah, why are the data symbols in the frequency domain?
But you say that sigma is a function of YR and C. Is that a type?
No, it's not a function of C.
It is the correlation matrix of your observations, right?
Yeah.
And it's a function of which channel you pick, so that's why we use this notation.
You pre-compute it, you don't have to compute it.
Right, because we're saying we're one of 6 of these channels, right? Those 6 channels, we said, it's delay spread 100 nanoseconds, 200 nanoseconds, 500, whatever it is, out to 1,100 nanoseconds. So once I say that, I have a uniform power delay profile with a certain delay spread, then I can compute my frequency domain correlations.
So what is the index R? What is LT? That's maybe where I'm getting.
LT is transmit antennas, so we've got this across transmit antenna. I'm sorry, I don't know why. I think there should both be LR. So LR is number of receive antenna. So you're basically combining the data from the receiver. So I think the T is a typo. I apologize for that.
And this, is it like a determinant of sigma in the first one?
Yes.
Log determinant?
Yeah. So I mean, it's just, realize that once, we have known data, known transmitted data, a Gaussian model. So it's a standard Gaussian PDF, right? So I mean, there's nothing powerful about this
So
here.
it looks like it can be implemented as a filter bank each filter for each sigma hypothesis, and then you just pick whatever has a minimum.
Exactly. So essentially, it's very simple to take the preamble, detect which your channel is, and then filter to that channel and get very close to optimum performance.
So you started with the idea that you're going to have these fixed candidates, right?
Yes.
Models, which are not exactly the same as the representative channel models A through F. That they're different.
Yes.
Right. Although there's 6 of them. Are you then going to somehow test if you choose one of the A through F, which one of your alternate 6 somehow captures its best? So you can do one kind of experiment. You say, well, I'll just choose one of my actual 6 models,
right,
and I'll see that I really find the right one, and that I.
Now, what I can say is that we've gone down that path, and we discovered it A through F, right, doesn't model real life randomly very well. So if we set our parameterization by A through F and we generate something that's significantly different from A through F, we end up not getting a good match and getting this error floor to happen. And so the reason we went to the uniform power delay profile is because that proved to be over a lot of simulations, not by me but by Wei Jun, a lot of simulations showing that was the most robust model.
It should be robust over some class of channel.
I mean, essentially some class of delay limited channels, right? I mean, assuming that most of your power is happening in small delays, then that's proved to be the most robust. So I mean, what I can say is, if we do the Soleil Valenzuela model, which is completely different than this, and we run it on this, then it still seems to work robustly. Okay. So that's sort of why we chose this thing that was, our first idea was, oh yeah, we'll just pick the A through E models as our parameterization, and then, gee, that'll work really well because we know it's one of A through E when we test. But what we found was when we went to something that wasn't those, then we had non-robust performance. That's why we went back to this uniform power delay profile.
So one of your message to the standards people is that your standard profiles are not good enough.
No, it just says that if I use that as a way to classify channels to filter, that's not a good way to classify channels to filter. It's from the point of view of realistic models of real propagation in real channels. I think these channels all come from channel sounding. If I remember right, they went out and did a big channel sounding experiment, and they said, okay, these look like channels that are typical of these environments. So I'm not saying that the channel models are full of hot air. They're clearly not. What I'm saying is that they're not robust to this frequency domain filtering. That's probably the better way of saying it.
Mike, I have a following question. Suppose you have these 6 models, and you are sending actually one of them. So you run a filter bank of 6, and then it will just return. Ideally, what you send will be detected. Now, what is the minimum? I mean, it certainly the accuracy of this detection depends upon the length of your Y sample, which you're putting in the calculation of the statistics. So what is like a typical length I need to really run this filter bank across so that with a confidence of, let's say, whatever, 99%, I will uncover or detect the what I sent?
Okay.
So how fast it converges in terms of the number of samples?
Okay, so this is a very busy slide, and I was hoping not to go through it but you ask a very good question. There's a couple observations we made that I'm hoping will answer this question because it came down to basically being, I mean, when we asked this same question, these were the answers that popped out, I guess is the way I'd say. The first thing is if you remember from before, we don't want to make a mistake, okay? And in fact, it's pretty clear we don't want to make a mistake to a smaller delay spread. That would be disastrous, right? Because then we'd be filtering out things that and not including them in the estimates. The other thing we found is you don't want to make a mistake at lower signal-to-noise ratio than really is in the channel. Okay, or excuse me, you don't want to make the design signal-to-noise ratio to be higher than the real signal-to-noise ratio. That's going to cause sort of disastrous things to happen. So what we found was, really you have to make your design signal-to-noise ratio fairly large. And what we found was, I think if we're within 5 dB, then we're reasonably good. Okay, so if you're matched, then basically what you get is something along this diagonal. And the one thing that you'll notice is we tend to go. Okay, I should say one other thing that we did. One other thing is we wanted to add in practice. Whatever we detect as our channel, we go with one bigger, just for robustness. Okay, that's an ad hoc thing, but we found it works pretty well. So what you can see is, so this is the channel number, and here's what we estimate. And you can see that, in general, this structure, we're always estimating a bigger channel than what we got. And so that gives us the robustness and performance. So I guess the final thing that I'd answer to answer your question is, these are with the typical 802.11 preambles. So it's 2 symbols in length of the channel, or 2 symbols for 2 antennas, or 4 symbols for 4 antennas. So that's what all the simulation is. So it shows that you can use very short packets and get good estimates of what the channel models are.
Actually, in the second, the last column of the second table, it looks like it's pretty much predicts with almost equal probability any of the channels.
Right. So that's what we're saying. This is a bad thing to do. Don't make your design SNR much bigger than your actual SNR. So I think there's
actually surprising. It's only the last channel which behaves extraordinarily bad compared to the previous ones. Right? It's worse than any other.
So, the takeaway is on a preamble as short as what you'd see in 802.11n, you can do a good job of estimating what the channel is. If you make sure you don't underestimate or overestimate the signal-to-noise ratio. We found that if you're within 5 dB, works well. And typically, whatever you estimate, add 1 to it in terms of the delay spread parameterization, and that also is very robust. Gives you much better robust performance. And essentially, the curves here show that you can get. I think these are the 2 ideal cases, and these are the adaptive ones, and you're fairly close to being as good as you can get in the adaptive case. Okay, so now sort of the what should I say, the PR talk, right? So we're trying to, as everybody else is trying to think about getting more money into our university, and one way to get this more money into the university is, say you have a center, okay? So the center, what is it that we really think is unique about UCLA? And that's that we have people doing theoretical research, people building experimental platforms, and people doing VLSI. So that's sort of why we think this is interesting. Again, our paradigm of how we're going. This is really a slide meant for industry. So any industry people that are here, you can see the industry input and the tech transfer output. Those are the important things, right? The Mimo Testbed Platforms. We have a bunch of different platforms, one of which is Bob McDonishrod's group is building it. That's at 5 gigahertz. We're working on 2.5, and we're trying to get down to one common set of test beds that we can all experiment across. So the idea here is that we had went out and built some radios with a company in San Diego, and then we got some baseband processors, both on transmit and receive side, and we've got real OFDM systems running. So our goal in doing this is, we wanted to somehow get automated radio testing. And so, the one thing I have to say, after having supervised students doing, field testing over a number of years, is the one thing I don't want is students out doing field testing, because it's very labor-intensive, boring, and it's the best way to get students discouraged about a PhD is to put them out doing field testing. So what we tried to do is figure out some way.
We have 2 students, and they're all finished their masters.
So what we tried to do is say, okay, if that's the boring part about it, the fun part about it is designing the algorithms and getting it all working. The boring part is out there moving antennas around trying to get realistic field test data. And the other thing we wanted to have was, this ability. We're part of a similar program as WINLAB is in terms of this NSF Testbed program, so it has to be remotely accessible to other users in the community. And of course, since we're funded by NSF, we have no money. So we have to figure out some way to achieve all these goals in a very cheap way. And so how do we do it? We do it by using Legos. Okay? So Lego, the Lego Mindstorm is the idea here. And Lego Mindstorm is a robotic system. Okay? So we can program the robots to move the antennas for us instead of the graduate students. And the students have fun programming, and they don't have to do any testing.
I was telling him to do this.
He prefers humans created.
Otherwise, we will have to graduate Lego blocks.
He's only faking mobility. And you have actual mobility.
Yes. So the cool thing about it is that the Lego robots themselves actually they have an Ethernet access. So basically it can be run through a JavaScript. It's enabled to run. We can also control the data acquisition, data transmission, and both transmit and receive robots all from a remote terminal. So we, in fact, I think you guys probably had your PI meeting a short time ago. We had ours, and we were in a building clear across campus doing the PI meeting, and we were showing Joe Evans the...
Can you emulate the Autobahn?
No, this is all for wireless LAN. So, so we just move and then stay stationary, and then move and stay stationary. The way I like to think about it is we're trying to get ergodic averages, right? And ergodicity in this wireless LAN environment is in space. So we want to move around in space to get our averages.
So how can you say how wide that is? We saw the picture.
Here's a mouse pad. Okay, so that, tabletop size, something like that. So that's, at 2.4 gigahertz where the wavelengths are that big, that's tens of wavelengths across.
So how far are they?
Well, we've gone as far apart as being in different rooms, and so.
But if you're going to fix them if they're remotely controlled, right?
All we have to have is an Ethernet connection, right? We basically plug the Ethernet connection into the laptop that has a USB port to this, and.
So are you going to have 2 units, or are you going to have several units, and then you can turn them off on depending?
No, we just have 2 units. That's our plan. We only have one transmitter, one receiver at this point, so we just have 2 Lego robots moving. Okay, so let's see. That's just a picture of the hardware, and this is a picture of 802.11n in practice. So again, it's basically transmission. We're taking data in non-real time. This is our channel, our frequency domain channel responses of 2 of our channels. This is our time domain receive signal. So you can see we have what looks like 8 packets that we've captured, and then we do decoding on each of these packets. It turns out that we have 8 packets, and we're doing 802.11a at 12 and 48 megabits, Alamudi plus convolutional code at 12 and 48 megabits, and then LDPC at 48 megabits. And I think if I could scroll down, which I can't because it's of course a movie, we'd also have LDPC at 120 megabits per second.
That was my question. Can you log on now?
I didn't set it up with the students.
So will you comment on transmit power, CDMs, noise speaker?
Okay. Let me go back. So I don't know if you can see this plot down here. This is our plot through the overall system. So our overall system EVM is about less than 5% through the whole system. So we can do 64 clamp pretty easily. We're running a little problem with phase noise when we try to do 256 clamp. Well, I shouldn't say a little problem. We run into a big problem with phase noise when we do 256 clamp. Let's see. The other question was transmit power. Our amplifier, we actually have the amplifiers in the radios capable of doing about, I believe the 1 dB compression point is like 28 dBm. And so, we typically back off about 10 dB from that when we transmit. And
3% EVM is around 20 dBm.
We always measure it in percentage, so I don't know what the
But
transmit.
you back down to transmit power, so 20 dB, 100 milliwatts.
Yeah, something like that. I should say the power is fully programmable. We have control over transmit receive gains in both stages. So if we want to go lower power, we could do that as well. But I think it's been like 18 dBm has been our average transmit power. Let's see, is that the only other?
Just a noise figure, probably.
Noise figure, I'm thinking it's around 5, but I don't remember exactly. So. I can't say that I had any part in doing this. It was a company in San Diego that I'd worked with them on a previous project, and they did a pretty nice job of putting this together for us. Okay, well that's really all I had to say.
So if you go back to the big picture, they all, probably one or two exceptions, most of us here fit in that the loop of design, simulate, and now you're going that other loop, right?
Right.
Is there some truth you've learned that that those of us stuck in the other loop haven't shared?
No. What I'll say is, I think I'm just getting to the point where we can actually say something useful. I don't think I've said anything useful so far. But I think, as we try to push more and more bits per second, I think the bits per second per hertz, I think the channel model is going to become more and more important. Especially, I think really when we start going to networking kinds of issues, then the channel model is really going to become important, because the networking paradigm by itself is directional, and we need to figure out how that works with the channel model. I think the only thing I would make two comments. I think students seem much more energized when they actually see something of their own working. That's been a fun thing. I've done this both with my graduate students as well as teaching project courses, and they get pretty energized by seeing them teach. And the other thing I'd say is good theory works in practice, right? So, I always was a believer in theory, but I'm more of one now, because anytime something doesn't work, it's because you missed something in the theory, not because you missed, not because real life doesn't behave like theory says it is. I think there's strange things like
in the theory failed to model something important.
Yes, or you forgot to model something important. So that would be the statement. So I don't feel like I've changed how I do research any more than I don't feel like I do research any different than I did it 7 years ago. But I feel like I've learned a lot in doing this in some sense. I'm not sure it didn't result in a whole lot of journal papers or anything.